हे गाइस व्हाट्सअप, क्या हाल चाल? तो कैसे हो आप सब? तो आज हम लोग रीड करने वाले हैं मोशन इन स्ट्रेट लाइन। ठीक है, तो फिजिक्स का चैप्टर 3 रीड करने वाले हैं। क्लास 11th का है ना, तो चलो रीड करते हैं। तो हमें अपने रूम में पहुंच गए हैं। ठीक है, और सब बढ़िया भाई साहब। चलो रीड करते हैं यार। रीड करने में बहुत मेहनत लगती है और बहुत टाइम लगता है, प्लस एडिटिंग करने में। ठीक है, तो लाइट वाइट देखो नहीं आई है। इन्वर्टर इन्वर्टर से बल्ब जलाए हैं, एक बल्ब और जला ले रहे हैं। अब थोड़ा अच्छा लग रहा है देखने में। ठीक है, तो चलो स्टडी करते हैं। चैप्टर 3, मोशन इन स्ट्रेट लाइन। इंट्रोडक्शन। इंट्रोडक्शन ये है टॉपिक है। ठीक है, इंट्रोडक्शन, पोजीशन, path length and displacement, average velocity and the average speed, instantaneous velocity, speed, instantaneous acceleration, kinematic equation for uniformly accelerate motion, relative velocity, summary, point to ponder exercise, additional exercise, appendix 3.1. Okay. Introduction. Motion is common to everything in the universe. We walk, run, and ride a bicycle. Even when we are sleeping, air moves into and out from the lungs, and blood flows in arteries and veins. We see leaves falling from the trees and water flowing down a dam. Automobile and planes carry people from one place to the other. The earth rotated once every 24 hours and revolved around the sun once in a year. The sun itself is in motion in the Milky Way, which is again moving within its local group of galaxies. Motion is change to position of an object with time. How does the position change with time? In this chapter, we shall learn how to describe motion. For this, we develop the concept of velocity and acceleration. We shall confine ourselves to the study of motion of object along a straight line, also known as rectilinear motion. For the case of rectilinear motion with uniform acceleration, a set of simple equations can be obtained. Finally, to understand the relative nature of motion, we introduce the concept of relative velocity. In our discussion, we shall treated the object in motion as a point object. This approximation is valid so far as the size of the object is much smaller than the distance it moves in a reasonable duration of time. In a good number of situations in real life, the size of object can be neglected and they can be considered as a point-like object without much error. In kinematics, we study ways to describe motion without going into the cases of motion. What causes motion described in this chapter, and the next chapter forms the subject matter of chapter 5. Position, path, length, and displacement. Earlier, you learned the motion is the change in position of an object with time. In order to specify position, we need to use a reference point and a set of axes. It is convenient to choose the rectangular coordinated system consisting of three mutual perpendicular axes labeled x, y, and z axes. The point of intersection of these three axes is called origin and serve as the reference point. The coordinate x, y, z of an object describe the position of object with respect to this coordinate system. To to measure time with position a clock. In this system, this coordinate system along with a clock constituent a frame of reference. If one or more coordinate of an object change with time, we say that the object is in motion. Otherwise, the object is said to be at rest with respect to this frame of reference. The choice of a set of axes in a frame of reference depend upon the situation. For example, for describing motion in one dimension, we need only one axis to describe motion in 2 3 dimensions. We need a set of 2 3 axes. Um, Description of an event depend on the frame of reference chosen for the description. For example, when you say that a car is moving on a road, you are describing the car with respect to a frame of reference attached to your or to the ground, but with respect to a frame of reference attached with a person sitting in the car, the car is at rest. To describe motion along a straight line, we can choose an axis, say x-axis, so that it coincides with the path of the object. We then measure the position of the object with reference to a conventionality, chosen origin, say, or as so in figure 3.1. Position to the right of O are taken as positive and to the left or left of O as negative. Following this convention, the position coordinate of point P and Q in figure 3.1 are plus 360 meter and plus 240 meter. Similarly, the position coordinate of point R is minus 120 meter. Path length. Consider the motion of a car along a straight line. We choose the x-axis such that it coincides R O Q P. X-axis origin and position of a car at different time. 160 minus x, 120 minus 80 minus 40 0, 40 80 120 160 200 240 280 320 360 400 meter plus x. With the path of the car's motion and origin of the axis as the point from where the car started moving, the car was at x equal to 0 at t equal to 0. Let P, Q and R represent the position of the car at different instant of time. Consider 2 cases of motion. In the first case, the car moves from O to P. Then the distance moved by the car is OP is equal to plus 360 meter. This distance is called the path length traversed by the car. In the second case, the car moves from O to P and then moves back from P to Q. During this course of motion, the path length transverse is OP plus PQ is equal to plus 360 meter plus 120 meter is equal to plus 480 meter. Path length is a scalar quantity, a quantity that has a magnitude only and no direction. See chapter 4. Displacement. It is useful to define another quantity, displacement, as the change in position. Let x1 and x2 be the position of an object at time t1 and t2. Then its displacement denoted by del x in time del t is equal to t2 minus t1 is given by the difference between the final and the initial positions. Del x is equal to x2 minus x1. We used the Greek letter delta. The delta to denote change in a quantity. If x2 greater than x1, del x is positive, and if less x2 less than x1, mm, del x is negative. Displacement has both magnitude and directions. Such quantities are represented by vector. You will read about vector in the next chapter. Presently we are dealing with motion along a straight line, also called rectilinear motion. Only in a one-dimensional motion, the one there are only two directions: backward and forward, upward and downward, in which an object can move, and these two directions can easily be specified by plus and minus sign. For example, displacement of the car in moving from O to P is this is del x is equal to x2 minus x1 is equal to plus 360 meter minus 0 meter is equal to plus 360 meter. The displacement has a magnitude of 360 meter and is directed in the positive x direction as indicated by the plus sign. Similarly, the displacement of the car from P to Q is 240 meter minus 360 meter is equal to minus 120 meter. The the negative sign indicates the direction of displacement. Thus, it is not necessary to use vector notation for discussing motion of object in one dimension. The magnitude of displacement may or may not be equal to the path length transversed by an object. For example, for motion of the car from O to P, the path length is plus 360 meter and the displacement is plus 360 meter. In these cases, the magnitude of displacement 360 meter is equal to the path length 360 meter. But consider the motion of car from O to P and back to Q. In these cases, the path length is equal to plus 360 meter plus 120 meter is equal to 480 meter. However, the displacement is equal to plus 240 meter minus 0 meter is equal to plus 240 meter. Thus, the magnitude of displacement 240 meter is not equal to the path length 480 meter. The magnitude of the displacement for a course of motion may be zero, but the corresponding path length is not zero. For example, if the car starts from O, goes to P, and then return to O, the final position coincides with the initial position and the displacement is zero. However, the path length of this journey is OP plus PO is equal to 360 meter plus 360 meter is equal to 720 meter. Motion of an object can be represented by a position time graph, as you have already learned about it. Such a graph is a powerful tool to represent and analyze the different aspects of motion of an object. For motion along a straight line, say x-axis and x-axis only, x coordinated varies with time, and we have an x minus t graph. Let us first consider the simple case in which an object is stationary. Example: a car standing still at x equal to 40 meter. The position time graph is a straight line parallel to the axis as shown in figure 3.2. If an object moving along the straight line cover equal distance in equal intervals of time. It is said to be in a uniform motion along a straight line. So the position time graph of such a motion. Position time graph, a stationary object, and B, an object in uniform motion. Position time graph of a car. Now let us consider the motion of a car that start from rest at time t equal to 0. Yes, from the origin O and peak up speed till t equal to 10 second, and thereafter moves with uniform speed till t equal to 80 second. Then the brake are applied and the car stop at t is equal to 20 second and x is equal to 296 meter. The position time graph for these cases is shown in figure 3.3. We shall refer to this graph in our discussion in the following section. Average velocity and average speed. When an object is in motion, its position changes with time, but how fast is the position changing with time and in what discuss to velocity, what direction, what direction to describe this. We define the quantity, average, नहीं यहाँ पर. We define the quantity average velocity. Average velocity is defined as the change in position or displacement del x divided by the time intervals del t in which the displacement occurs. Average velocity, v cap is equal to x2 minus x1 upon t2 minus t1 is equal to del x upon del t, where x2 and x1 are the position of the object at time t2 and t1 respectively. Here the bar over the symbol for velocity is a standard notation used to indicate an average quantity. The SI unit of velocity is meter per second, or meter per second, although kilometer per hectare is used in many every applications. Like displacement, average velocity is also a vector quantity, but as explained earlier, for motion in a straight line, the directional aspect of the vector can be taken care of by positive and negative sign, and we do not have to use the vector notation for velocity in this chapter. Consider the motion of the car in figure 3.3. The portion of the xt graph between t is equal to 0 second and t is equal to 8 second is blown up and shown in figure 3.4 as seen from the plot. The average velocity of the car between time t is equal to 5 second and t is equal to s second is v cap is equal to x2 minus x1 upon t2 minus t1 is equal to 27.4 minus 10 upon 7 minus 5 second is equal to 8.7 meter per second. Geometrically, this is the slope of the straight line P1 P2 connecting the initial position P1 to the final position P2 as shown in figure 3.4. The average velocity can be positive or negative depending upon the sign of the displacement. It is 0 if the displacement is 0. Figure 3.5 showing the xt graph for an object moving with positive velocity, moving with negative velocity, and at rest. Figure 3.5 c. Figure 3.5 position time graph for an object first moving with positive velocity, and b moving with negative velocity, positive velocity, negative velocity. And at rest, c rest. Average velocity as defined above involves only the displacement of an object. We have seen earlier that the magnitude of displacement may be different from the actual path length. To describe the rate of motion over the actual path, we introduce another quality called average speed. Average speed is the defined as the total path length traveled divided by the total time involved during which the motion has taken place. Average speed is equal to total path length upon total time interval. Average speed has obviously the same unit meter per second as positive at as that of velocity, but it does not tell us in what direction an object is moving. Thus, it is always positive. It is a constant contrast to the average velocity with which can be positive or negative. If the motion of an object is along a straight line and in the same direction, the magnitude of displacement is equal to the total path length. In that case, the magnitude of average velocity is equal to the average speed. This is not always the case, as we'll see in the following example. The average velocity is the slope of line P1 P2. Example. Example 3.1. A car is moving along a straight line, says OP in figure 3.1. It moves from O to P in 80 degrees Celsius, 80 seconds, and return from P to Q in 6 seconds. What are the average velocity and average speed or time of the car to going from O to Q and B from O to P and back to Q? Answer. Average velocity is equal to displacement upon time. V cap is equal to plus 360 meter upon 80 second is equal to plus 20 meter per second, plus 20 meter per second. Average speed is equal to path length upon time interval, is equal to 360 meter upon 80 second is equal to 20 meter per second. Thus, in this case, the average speed is equal to the magnitude of the average velocity. B. In this case, average velocity is equal to displacement upon time interval is equal to plus 240 meter in upon 18 plus 6 second. Average speed is equal to path length upon time interval is equal to OP plus PQ upon del T, 360 plus 120 upon 40 second. is equal to 20 meter per second. Thus, in this case, the average speed is not equal to magnitude of the average velocity. This happens because the motion here involve a change in direction, so that the path length is greater than the magnitude of displacement. This so that speed is in general greater than the magnitude of the velocity. If the car in example 3.1 move from O to P and comes back or to O in the same time interval, average speed is 20 meter per second, but the average velocity is 0. Instantaneous velocity and speed. The average velocity tell us how fast an object has been moving over a given time interval, but does not tell us how fast it moves at a different instant of time during that interval. For this, we define instantaneous velocity, or simply velocity v at instant t. The velocity at an instant is defined as the limit of the average velocity as the time interval del t, because डिफी सिमिलरली स्मॉल नहीं, यह इनफाइनाइटली सिमिलरली है स्मॉल इन अदर वर्ड्स. v equal to lime del x upon del t is move on 0 is equal to v equal to dx upon dt, where the symbol del t forward direction 0 standard for the operation of taking limit as del t is forward of the quantity on its right. In the language of calculus, the quantity on the right hand side of equal 3.3a in is the differential coefficient of x with respect to t, and is denoted by del x upon del t. See appendix 3.21. Okay, it is the rate of change of position with respect to time at that instant. We can use for obtaining the value of velocity at an instant either graphically or numerically. Suppose that we want to obtain it graphically, the value of velocity at t is equal to 4 second. Point P for the motion of the car represented in figure 3.3. Figure has been redrawn in figure 3.6, choosing different scales on scales to facilitate the determining velocity from the position. The graph velocity at small t is equal to 4 second is the slope of the tangent to the graph at that instant. Calculation. Let us take del t is equal to 2 second, centered at t is equal to 4 second. Then by the definition of the average velocity, the slope of line p1 p2 give the value of average velocity over the interval 3 second to 5 second. Now we decrease the value of del t from 2 second to 1 second. Then line p1 p2 becomes q1 q2, and its slope give the value of the average velocity over the interval 3.5 second to 4.5 second. In the limit del t is equal to 0, the line p1 p2 becomes a target to the position time curve at the point p, and the velocity at t is equal to 4 second is given by the slope of the tangent at that point. It is difficult to show this process graphically, but if we use numerical method to obtain the value of the velocity, the meaning of the limiting process becomes clear. For the graph shown in figure 3.6, x equal to 0.08 tq. Table 3.1 gives the value of del x upon del t calculated for del t equal to 2.0 second, 1 second, 0.5 second, 0.1 second, and 0.01 second. Center at t is equal to 4.0 second. The second and third column give the value of t1 is equal to t minus del t upon 2, and t2 is equal to t plus del t upon 2, and the fourth and the fifth column give the corresponding value of x. Example, x t1 is equal to 0.08 t1 t1 tq, and x t2 is equal to 0.08 t2 T2Q. The sixth column lists the difference del x is equal to x T2 minus x T1, and the last column gives the ratio of del x and del t, the average velocity corresponding to the value of del t list in the first column. We see from table 3.1 that as we decrease the value of del t from 2.0 second to 0.010 second, the value of the average velocity approaches the limiting value 3.84 meter per second, which is the value of velocity at t is equal to 4 second. The value of dx upon dt at t is equal to 4 second. In this manner, we can calculate velocity at each instant for the motion of the car. So in figure 3.3, for this case, the variation of velocity with time is found to be as shown in figure 3.7. Velocity, the graph corresponding to motion. So in figure 3.3, 30, 50, 30, 25, 20, 15, 10, 5, 0, 0, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 times second. Value meter per second. Velocity meter per second. The graphical method for the determination of the instantaneous velocity is always not a convenient method. For this, we must carefully plot the position time graph and calculate the value of average velocity as del t become smaller smaller and smaller. It is easier to calculate the value of velocity at different instant if we have data or position at different instant or extra expression for the position as a function of time. Then we calculate del x upon del t from the data for decreasing the value of del t, and find the limiting value as we have done in table 3.1, or use differential calculus for the given expression and calculate dx upon dt at different instant as done in the following example. Limiting a value of del x upon del t at t is equal to 4 second. Del t second, t1 second, t2 second, x t1 t1 मीटर में, x t2 मीटर, x del x मीटर, del x अपॉन del t मीटर पर सेकेंड। 2 2 3 2 3 5 1 3.5 4.5 0.5 3.75 equal to 4.25 0 1 3.95 4.05 0.01 3.995 is equal to 4.05. 2.16 10 7.84 and 3.92 3.43 7.29 3.86 3.86 4.21 875 6.14125 1.9225 3.845 4.93039 5.3141441 0.38402 3.8402 5.10 5.1000824 5.139224 0.0384 3.84 3.8400. Example: the position of an object. Example 3.2. The position of an object moving along x-axis is given by x is equal to a plus bt square, where a is equal to 8.5 meter, b is equal to 2.5 meter per second, second square, and t is measured in second. What is its velocity at t is equal to 0 second, at t is equal to 0 second? What is the average velocity between t2 is equal to 2.0 second and t is equal to 4.0 second? Answer: in notation of differential calculus, the velocity is v is equal to 4x upon dt is equal to d upon dt a plus bt square is equal to 2 bt is equal to 5.0 t meter per second. At t is equal to 0 second, v is equal to 0 meter per second, and at t is equal to 2 second, v is equal to 10 meters per second. Average velocity is equal to x 4 point minus x 4.0 minus x 2.0 upon 4.0 minus 2.0 is equal to a plus 16b minus a minus 4b upon 2.0 is equal to 6.0 into b is equal to 6.0 into 2.5 is equal to 15 meter per second. From figure 3.7, we note that during the period t is equal to 10 second to 18 second, the velocity is constant. Between period t is equal to 18 second to t is equal to 20 second, it is uniformly decreasing, and during the period t is equal to 0 second to t is equal to 10 second, it is increasing. Note that for uniform motion, velocity is the same as the average velocity at all instants. Instantaneous speed, or simply speed, is the magnitude of velocity. For example, a velocity of plus 24 meter per second and a velocity of minus 24 meter per second both have an associated speed of 24 meter per second. It should be noted that through average speed over a 15 interval of time is greater or equal to the magnitude of the average velocity. Instantaneous speed at an instant is equal to the magnitude of the instantaneous velocity at the instant. Why so? Acceleration, the velocity of an object in general changes during its course of motion. How to describe the change should be described as the rate of change in velocity with distance or with time. This problem a problem even in Galileo times. It was first tough that this change could be described by the rate of change of velocity with distance, but through his studies of motion of freely falling object and motion of object on an inclined plane, Galileo concluded that the rate of change of velocity with time is a constant of motion for all objects in free fall. On the other hand, the change in velocity with the distance is not constant. It decreases with the increased distance of fall. This led to the concept of acceleration as the rate of change of velocity with time. The average acceleration a cap over a, a इसको बोलते हैं the average acceleration vector a over a time interval is defined as the change velocity derived by the time interval. Vector A is equal to V2 minus V1 upon T2 minus T1 is equal to del V upon del T, where V2 and V1 are instantaneous velocity or simply velocity at time. T2 and T1 it is the average change of velocity per unit time. The SI unit of acceleration is meter per second square. On a plot of a velocity versus time, the average acceleration is the slope of the straight line connecting a two point corresponding to and the average acceleration for velocity time graph. So in figure 3.7 for different time intervals 0 second to 10 second, 10 second minus 18 second, and 18 second to 20 seconds are 0 second to 10 second. Vector A is equal to 24 minus 0 meter per second upon 10 minus 0 second is equal to 2.4 meter per second square. 10 second to 10 second to 18 second acceleration is equal to 24 minus 24 meter per second upon 18 to 10 second. 80 minus 10 second is equal to 0 meter per second. 18 second to 20 second vector A is equal to 0 minus 24 meter per second upon 20 minus 20 minus 18 second is equal to minus 12 meter per second. Acceleration as functions of time for motion represented in figure 4.8 2.40 minus 2.4 minus 4.8 minus 7.2 minus 9.0 minus 12.0 2 4 6 8 10 12, 14, 16, 18, 20, and 22 t second times a acceleration meter per second square. Instantaneous acceleration is defined in the same way as the instantaneous velocity. Acceleration is equal to acceleration a is equal to lime del v upon del t, del t in forward zero forward direction, del v upon del t. The acceleration at an instant is the slope of the tangent to the Vt curve at that instant. For the Vt curve shown in figure 3.7, we can obtain acceleration at every instant of time. The resulting a minus t curve is shown in figure 3.18. We see that the acceleration is non non-uniform over the period 0 to 10 second. It is 0 between 10 second and 18 second, and is constant with the value minus 12 meter per second square between 18 seconds and 20 seconds. When the acceleration is uniform, obviously it equal to average acceleration over that period. Since velocity is a equality velocity is a quantity have both magnitude and direction. A change in velocity may involve either or both of these factors. Acceleration therefore may result from a change in speed, magnitude, a change in direction, or a change in both. Like velocity, acceleration can also be positive, negative, or zero. Position time graph for motion with positive, negative, and zero acceleration are shown in figure 3.9 A, B, and C respectively. Note that the graph curve upward for positive acceleration, downward for negative acceleration, and it is a straight line for zero acceleration. As an exercise, identify in figure 3.3 the regions of the curve that correspond to these three cases. Although acceleration can vary with time, our study in this chapter will be restricted to motion with constant acceleration. In this case, the average accelerations equal the constant value of acceleration during the interval. If the velocity of an object is v naught and t is equal to 0, and v at time t, we have a vector a is equal to v minus v naught upon t minus 0, or v is equal to v naught plus a t. Position time graph for motion with a positive acceleration, b negative acceleration, c zero acceleration. Let us see how velocity and time graph look like for some simple cases. Figure 3.10 so velocity time graph for motion with constant acceleration for the following cases. An object is moving in a positive direction with a positive acceleration. For example, the motion of the car in figure 3.3 between t is equal to 0 second and t is equal to 10 second. B. An object is moving in positive direction with a negative acceleration. For example, motion of the car in figure 3.3 between t is equal to 18 second and 20 second. An object is moving in a negative direction with a negative acceleration. For example, the motion of a car the moving from O in figure 3.1 in a negative x direction with increased speed. D. An object is moving in positive direction until time t1 and then turn back with the same negative acceleration. For example, the motion of a car from point O to point Q in figure 3.1 till time t1 with decreasing speed and turning back and moving with the same negative acceleration. An interesting feature of velocity time graph for any moving object is that the area under the curve represents the displacement over a given time interval. A general proof of this from this velocity velocity time graph for motions with constant acceleration. A motion in positive direction. B motion in positive direction with positive acceleration. B motion in positive direction with negative acceleration. Positive direction, negative acceleration. B. C motion in negative direction with negative acceleration. Negative direction with negative acceleration. D. Motion of an object with negative acceleration that change direction at time t1 between t1 between times 0 to t1 it moves in positive x direction, and between t1 and t2 it moves in the opposite direction. Statement required use of calculus. We can, however, see that is true for the simple case of an object moving with constant velocity u. Its velocity time graph is as shown in figure 3.11. Figure 3.11. Area under VT curve squirrel displacement of the object over a given time interval. The VT curve is a straight line parallel to the time axis, and the area under it between t is equal to 0 and t is equal small t is equal to capital T is the area of rectangle of height u and base t. Therefore, area is equal to u into t is equal to ut, which is the displacement in this time interval. How come in this case an area is equal to a distance? Think. Note the dimension of quantities on the two coordinate axes, and you will arrive at the answer. Note that the xt, vt, and at graph shown in several figures in this chapters have sharp connects at some point, implying that the functions are not differentiable at these point. In any realistic situation, the functions will be differentiable at all points, and the graph will be smooth. What this means physically is that acceleration and velocity cannot change value ab- abruptly at an instant. Change are always continuous. Kinematic equation for uniformly accelerated motion. For uniformly accelerated motion, we can derive some simple equation that related displacement x, time taken small t, and instant velocity v, not final velocity v. and acceleration A. Equation 3.6 already obtained gives a relation between final and initial velocity v and v naught of an object moving with uniformly acceleration A. V is equal to V naught plus AT. This relation is graphically represented in figure 3.12. The area under this curve is area between instant O and T is equal to area of triangle ABC plus area of rectangle OACD is equal to half v minus v naught t plus v naught t. Area under Vt curve for an object with uniform acceleration. As example in the previous section, the area under Vt curve represent the displacement. Therefore, the displacement x or of the object is x is equal to 1 by 2 v minus v naught t plus v naught t v but v minus v naught is equal to at. Therefore, x is equal to 1/2 at square half at square plus v naught, or x is equal to v naught t plus half at square. Equation 3.7 can also be written as x is equal to v plus v naught upon 2 t is equal to vector v t, where vector v is equal to v plus v naught to constant acceleration only. Equation 3.9a and 3.9b mean that the object has undergone displacement x with an average velocity equal to the arithmetic average of the initial and final velocity. From equation 3.6, t is equal to v minus v naught upon a, substituting this in equation 3.9a, we get x is equal to vector vt is equal to v plus v naught upon 2 v minus v naught upon a is equal to v square minus v naught square upon 2a. V square is equal to v naught square plus 2ax. This equation can also be obtained by substituting the value of t from equation 3.6 into equation 3.8. Thus, we have obtained three important equations. V is equal to v naught plus at, x is equal to v naught t plus 1/2 at square. V square is equal to v naught square plus 2ax. Connecting five quantities v naught v a t and x. These are kinematic equation of rectilinear rectilinear motion of constant acceleration. The set of equation 3.11a were obtained by assuming that at t is equal to 0 the position of the particles x is 0. We can obtain a more general equation if we take the position coordinate at t is equal to 0 as non-zero. It says yes not, says yes not. Then equations 3.11a are modified, replacing x by x minus x naught to v is equal to v naught plus 8, x is equal to x naught plus v naught plus v naught t plus 1/2 at square. V is equal to v square is equal to v naught square plus 2a in bracket में x minus x naught. Example 3.3 obtained equation of motion for constant acceleration using a method of calculus. Answer by definition, acceleration is equal to del v upon del t, and del v is equal to a a a dt, integrating both side. Mm, Work done v naught dv is equal to work done t t0 a t dt is equal to a is equal to work done t0 dt. A is constant. V minus V naught is equal to 80. V is equal to V naught plus 80. Further, V is equal to dx upon dt. Dx is equal to dx is equal to V dt, integrating both side. X naught dx is equal to V dt. Work done T0 V naught plus 80 dt 80 dt. X minus x naught is equal to V naught t plus half 80 square. X is equal to x naught plus V naught t plus 1 half 80 square. We can write a is equal to del v upon del t is equal to d dv upon dx, dx upon dt is equal to v dv upon dx, or v dv is equal to a dx, integrating both side. Summation v v naught v dv is equal to work done x naught a dx. V is equal v square minus v naught square upon 2 is equal to a x minus x naught. V square is equal to v naught square plus 2 x minus x naught. The advantage of this method is that it can be used for motion with non-uniform acceleration also. Now we shall use these equation to some important cases. Example. Example 3.4, a ball is thrown vertically upward with a velocity of 20 meter per second from the top of a multi story building. The height of the point from where the ball is thrown is 25.0 meter from the ground. A. How high will the ball rise, and b, how long it be before the ball hits the ground. Take g is equal to 10 meter per second. Answer a. Let us takes the y-axis the vertically upward direction with 0 at the ground, as so in figure 3.3. Now v naught is equal to plus 20 meter per second. A is equal to minus g is equal to minus 10 meter per second. V is equal to 0 meter per second. If the ball rises to height v from the point of launching, then using the equation v is equal to v square is equal to v naught square plus 2a y minus y naught, we get 0 is equal to वो है ना वो है 0 o is equal to O is equal to 20 square plus 2 minus 10 y minus y naught. Solving, we get y minus y naught is equal to 20 meter. B. We can solve this part of the problem two ways. Note carefully the method used. First method. In the first method, we split the path in two parts: the upward motion A to B and the downward motion B to C, and calculate the corresponding time take t1 and t2. Since the velocity at b is 0, we have v is equal to v naught plus at, and o is equal to 20 minus 10 t1, and t1 is equal to 2 second. This is the time in going from A to B. From B or the point of the maximum height, the ball fall free under the acceleration due to the gravity. The fall is moving in negative y direction. We used equation y is equal to y naught plus v naught t plus half at square. We have y naught is equal to 45 meter, and y is equal to 0, and v naught is equal to 0, and a is equal to minus g, uh, minus g is equal to minus 10 meter per second square. O is equal to 45 plus 1 by 2 minus 10 t2 square. Solving we get 2 is equal to 3 second. Therefore the total time taken by the ball before it hits the ground, t1 t1 the t2 is equal to 2 yes 2 years 2 second plus 3 second is equal to 5 second. Second method, the total time taken can also be calculated by nothing the coordinate of initial and final position of the ball with respect to the origin chosen, and using equation y is equal to y naught plus v naught t plus half at square. Now y is equal to 2. Now y is equal to 25 meter, 25 meter, g is equal to 0 meter, and v naught is equal to 25 meter per second, and a is equal to minus 10 meter per second square. T is equal to 0. 0 o is equal to 25 plus 20 t plus half minus 10 t square, or 5 t2 minus 20 and 20 t minus 25 is equal to 0. Solving this quadratic equation for t, we get t is equal to 5 second. Note that the second method is better, since we do not have to worry about the path of the motion, as the motion is under constant acceleration. Example 3.5 free fall. Discuss the motion of an object under free fall. Neglected air resistance. Answer: an object released near the surface of the earth is accelerated downward under the influences of the force of gravity. The magnitude of acceleration due to gravity is represented by g. If air resistance is neglected, the object is said to be in free fall. If the height through which the object fall is small compared to the earth radius, g can be taken to be constant, equal to 9.8 meter per second square. Free fall is thus a case of motion with uniform acceleration. We assumed that the motion is in y direction, more correctly in y direction, because we choose upward direction as positive, since the acceleration due to gravity is always downward. It is the negative direction, and we have is a is equal to minus g is equal to minus 9.8 meter per second square. The object is released from rest at y is equal to 0. Therefore v naught is equal to 0, and the equation of motion becomes v is equal to o minus gt. is equal to minus 9.8 t meter per second. Y is equal to O minus half half gt square is equal to minus 4.9 t square meter. V2 is equal to 0. V2 is equal to O minus 2gy is equal to minus 19.6 y meter square second square. These equation gives the velocity and the distance travel as a function of time, and also the variation of velocity with the distance, the variation of acceleration, velocity, and distance with the time have been plotted in figure 3.14a, b, and c. A, B, and C. Mm, Figure 3.14, motion of an object under free fall. Various variation of acceleration with time, and B, variation of velocity with time. Velocity with time, variation of velocity with time. And C, variation of distance with time. Example 3.6, Galileo's law of odd number. The distance traveled during equal intervals of time by a body falling far rest state stand to one another in the same ratio as the odd number, beginning with unity, namely 1 ratio 3 ratio 5 ratio 7 dot dot dot. Prove it. Answer. Let us divide the time interval of motion of an object under free fall into many equal intervals, tau, and find out of distance distance travel distance traversed during successive intervals of time. Since the initial velocity is 0, we have y is equal to minus half gt square. Using the equation, we can calculate the position of the object after different time intervals, o tau, t tau, 3 tau, 0 से शायद 0 1 tau 2 tau 3 tau dot dot dot, which are given in the second column of table 3.2. If we take minus half gt square, g tau square as y naught is equal to the position coordinate after first time interval, tau. Then third column gives the position in the unit of y naught. The fourth column gives the distance transferred in successive tau second. We find that the distance are in the simple ratio 1 ratio 3 ratio 5 ratio 7 ratio 9 ratio 11 dot dot dot, as shown in the last column. This law was established by Galileo Galilei from 564 to 1642, who was the first to make a quantitative studies of free fall. Example 3.7, stopping distance of a vehicle. When brakes are applied to a moving vehicle, the distance it travel before stopping is called stopping distance. It is an important factor for road safety and depend on the initial velocity v naught and the braking capacity or deceleration minus a that is used by the braking drive and expressions for stopping distance of a vehicle in term of v naught and a. Answer. Let the distance traveled by the vehicle before it stops be d. Yes, then using equation of motion v2 square v naught square plus 2 to ax and nothing that v is equal to 0. We have the stopping distance vs is equal to minus v naught square upon 2a. Thus, the stopping distance is proportional proportional the square of the initial velocity, doubling the initial velocity increase the stopping distance by a factor of 4 for the same deceleration for the car of a perpendicular. The braking distance was found to be 10 meters, 20 meters, and 34 meters, and 50 meters, corresponding to velocities of 11, 15, 20, and 25 meter per second, which are nearly consistent with the above formula. Stopping distance is an important factor considered in setting speeds limits. For example, in school zone. Example 3.8 reactions time. When a situation demands our immediate action, it takes some time before we really respond. Reaction time is the time a person takes to observe, think, and act. For example, if a person is driving and suddenly a boy appear on the road, then the time is elapses before he slams the brakes of the car. Is the reactions time depend on complexity of the situation and on the individual. You can measure your reaction time by a simple experiment. Take a ruler and ask your friend to drop it vertically through the gap between your thumb and forefinger. Figure 3.15. After you catches it, find the distance traveled by the ruler. In a particular case, was d was found to be 11 centimeter. Estimate reaction time. Measuring the reaction time. Roll the hand. Ruler friend's hand. Answer: the ruler drop under free fall. Therefore, V naught is equal to 0 and A is equal to minus G is equal to minus 9.8 meter per second square. The distance traveled D and the reaction time T are related by D is equal to minus 1 by 2 G2 G square. G T R is equal to under root 2 D upon G second. Given D is equal to 21 centimeter and G is equal to 9.8 meter per second square. The reactions time is TR is equal to under root 2 into 0.21 upon 9.8 second is equal to 0.2 second. Relative velocity. You must be familiar with the experience of traveling in a train and being overtaken by another train moving in the same direction as you are. Will that train must be traveling faster than you to be able to pass you. It does seem slower to be than it would be to some standing on the ground and watching both the train In a case both the train have the same velocity with respect to the ground, then to you the other train would seem to be not moving at all. The understand such observation, we now introduce the concept of relative velocity. Consider two objects A and B moving uniformly with average velocity VA and VB in one dimension, say along the x-axis, unless otherwise specified. The velocities mentioned in this chapter are measured with reference to the ground. If x a 0 and x b 0 are position of object a b respectively at a time t is equal to 0, their positions x a t and x b t at time t are given by x a t is equal to x a 0 plus v a t, x b t is equal to x b 0 plus v b t. Then the displacement for object a to object b is given by x b a t is equal to x b t minus x a t is equal to x b 0 minus x a 0 plus VB minus VAT. Equation 3.13 is easily interpreted. Tell tell us that as seen from object B has a velocity mm, velocity VB minus VA because the displacement from A to B changes steadily by the amount VB minus VA in each unit of time. We say that the velocity of object B relative to object A is VB minus VA. VBA is equal to VB minus VA. Similarly, velocity of object A relative to object B is VAB is equal to VA minus VB. Position time graph of two objects with equal velocity. This show v VAB is equal to minus VAB. Now we consider some special cases. If VB is equal to VB minus VA is equal to 0, then from equation 3.13 xb t t minus x a t is equal to xb 0 minus x a 0. Therefore, the two objects stay at a constant distance xb 0 x a 0 apart, and their position time graph are in straight line parallel to each other as shown in figure 3.16. The relative velocity VAB or VBA is 0 in this case. B. If VA greater than VB, VB minus VA is negative. One graph is steeper than the other and they meet at a common point. For example, suppose the VA is equal to 20 meter per second and XA 0 is equal to 10 meter and VB is equal to 10 meter per second. XB 0 is equal to 40 meter. Then the time at which they meet is t is equal to 3 second. At this instant they are both at a position x a t is equal to x b t is equal to 70 meter. Thus object A overtake object B at this time. In this case VBA is equal to 10 meter per second minus the 20 meter per second is equal to minus 10 meter per second is equal to minus VAB. See, supposed VA and VB are of opposite sign. For example, if in the above example object A is moving with 20 meter per second starting at xa 0 is equal to 10 meter, and the object B is moving with 10 minus 10 meter second starting at xb 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 0 is equal to 10 xbo is equal to 14 meter. The two objects meet at t is equal to 1 second. Figure 3.18, the velocity of B relative to A, V BA is equal to minus 10 minus 20 meter per second is equal to minus 13 meter per second, or is equal to minus VAB. In this case, the magnitude of VBA or VAB is equal to 13 meter per second is greater than the magnitude of velocity of A or B, that of B, if the object under consideration are two train, then for a person sitting on either of the two, the other train seem to go very fast. Note that equation 3.14 are valid even if VA and VB represent instantaneous velocities. Position time graph of two objects with an equal velocity showing the time of meeting. Position time graph of two objects with velocity in opposite direction showing the time of meeting. Example 9.3.9, two parallel rail track run north to south. Train A move north with a speed of 54 kilometers per hour, and train B moves south with a speed of 9 kilometers per hour. What is the A velocity of B with respect to A? B velocity of ground with respect to B, and C velocity of a monkey running on the roof of train A against its motion with a velocity of 18 km per hour with respect to the train A, as observed by a man standing on the ground. Answer: choose the positive direction of x-axis to be from south to north. Then VA is equal to plus 54 kilometer per hour is equal to 15 meter per second. VB is equal to minus 90 kilometer per hour is equal to minus 25 meter per second. The relative velocity of B with respect to A is equal to VB minus VA is equal to minus 40 meter per second. The train B appears to move with a speed of 40 meter per second from north to south. Relative velocity of ground with respect to B is equal to 0 minus V is equal to O minus VB is equal to 25 meter per second. In C, let the velocity of the monkey with respect to ground be Vm, relative velocity of monkey with respect to A. Vma is equal to Vm minus Va is equal to minus 18 kilometer per hour is equal to minus 5 meter per second. Therefore, um is equal to 15 minus 5 meter per second is equal to 10 meter per second. Summary: an object is said to be in motion if its position changes with time. The position of the object can be can be specified with to mm, reference to a conveniently chosen origin for motion in a straight line. Position to the right of the origin is taken as positive, and to the left as negative. Path length is defined as the total length of the path transferred by an object. Displacement is the change in position del x is equal to x2 minus x1. Path length is greater or equal to the magnitude of the displacement between the same point. An object is said to be uniform motion in a straight line if its displacement is equal in equal intervals of time. Otherwise, the motion is said to be non-uniform. Average velocity is the displacement derived by the time interval in which the displacement occurs. Vector v is equal to del x upon del t. On an xt graph, the average velocity over a time interval is the slope of the line connecting the initial and final position corresponding to that interval. Average speed is the ratio of total path length traversed and the corresponding time interval. The average speed of an object is greater or equal to magnitude of the average velocity over a given time interval. Instantaneous velocity, or simply velocity, is defined as a limit of the average velocity as the time intervals del t becomes infinitesimally small. V is equal to line vector v del t direction. Lime del x upon del t, del t forward o x del x upon del t. The velocity at a particular instant is equal to slope of the tangent drawn on position time graph at that instant. Average acceleration is change in velocity derived by the time interval during which the change occurs. A is equal to del V upon del T. Instantaneous acceleration is defined as limit of average acceleration as the time interval del T goes to zero. A is equal to lime vector A del forward O is equal to lime del V upon del T, del T forward O is equal to del V upon del T. The acceleration of an object at a particular time is the slope of the velocity time graph at that instant of time. For uniform motion, acceleration is zero, and the xt graph is a straight line inclined to the time axis, and the vt graph is a straight line parallel to the time axis for motion with uniform acceleration. The xt graph is a parabola wheel. The vt graph is a straight line inclined to the time axis. The area under the velocity time curve between time t1 and t2 is equal to the displacement of the object during that interval of time. For object in uniformly accelerated object linear motions. The five quantities displacement x, time taken t, initial velocity v naught, final velocity v, and the acceleration a are related by a set of a simple equation called kinematic equation of motion. V is equal to v naught plus at, x is equal to v naught t plus half at square. V square is equal to v naught square plus 2ax. If the position of the object at time t is equal to 0 is 0, if the particles start at x is equal to x naught and x in above equation is replaced by x minus x naught. Physical quantity symbol dimension unit remark path path length symbol नहीं दिया है dimension real unit मीटर remark displacement del x dimension L unit small m is equal to x2 minus x1 in one dimension. Its sign indicate the direction. Velocity average v no, vector v is equal to vector v uh, and instantaneous v dimension lt minus 1 and unit meter per second. And remark del x upon del t is equal to lime del x upon del t is equal to del x del t. Average instantaneous dimension lt minus 1 meter per second. Path length upon time interval dx upon dt. Acceleration average vector a instantaneous a dimension lt minus 2 meter per second square. Remark del v upon del t is equal to lime del v upon del t is equal to del v upon del t in one dimension. Its sign indicate the direction. Points to ponder. The path length transferred by an object between 2 points is in general not the same as the magnitude of displacement. The displacement depends only on the end point. The path length, as name implies, depend on the actual path in one dimension. The two quantities are equal only if the object does not change its direction during the course of motion. In all other cases, the path length is greater than the magnitude displacement. In view of point A1 above, the average speed of an object is greater than or equal to the magnitude of the average velocity over a given interval. The two are equal only if the path length is equal to magnitude of displacement. 3. The origin and the positive direction of an axis are a matter of choice. You should first specify this choice before you assign two quantities like displacement, velocity and acceleration. If a particle is speeding up, acceleration is in the direction of velocity. If its speed is speed is decreasing, acceleration is in the directions opposite to that the velocity. This statement is independent of the choice of the origin and the axis. The sign of acceleration does not tell us whether the particle's speed is increasing or decreasing. The sign of acceleration, as mentioned in point 3, depend on the choice of the positive direction of the axis. For example, if the vertically upward direction is chosen to be positive direction of the axis, the acceleration due to gravity is negative. If the particle is falling under gravity, this acceleration through the negative result in increase in speed. For a particle through upward, the same negative acceleration of gravity result is decrease in speed. The zero velocity of a particle at any instant does not necessarily imply zero acceleration at that instant. A particle may be marginally at rest and it have non-zero acceleration. For example, a particle thrown up has zero velocity and its uppermost point, but the acceleration at that instant continues to the acceleration due to gravity. In the kinematic equation of motion, equation number 3.11, the various quantities are algebraic. They many positive or negative. The equation are applicable in all situations. For one-dimensional motion with constant acceleration, provided in the value of different quantities are substituted in the equations with proper sign. The definition of instantaneous velocity and acceleration, equation 3.3 and 3.5 are exact and are correct. Will the kinematic equation 3 figure 3.11 are truly only for motion in which the magnitude of the direction of the acceleration are constant during the course of motion. तो यार यहाँ पर हम लोग का चैप्टर मोशन इन स्ट्रेट लाइन खत्म हो रहा है। ठीक है, रीडिंग समाप्त हो गया। हम मिलते हैं नेक्स्ट चैप्टर में। ठीक है, नेक्स्ट चैप्टर अपना है, इधर एक्सरसाइज दिया है, एक्सरसाइज बाद में करेंगे। ठीक है, क्वेश्चन दिया करेंगे बाद में। इधर नेक्स्ट चैप्टर अपना है, 1 मिनट। नेक्स्ट चैप्टर है मोशन इन ए प्लेन। ठीक, चैप्टर 4 है, इसको हम बाद में डिस्कस करेंगे। ठीक है, आज के लिए बस इतना ही।